The faint glow from far-off galaxies does not travel unchanged through the universe. As space itself expands, those original rays, once shining in visible or ultraviolet hues, are stretched into longer wavelengths, shifting deep into the infrared by the time they reach our detectors. The James Webb Space Telescope is specifically designed to capture this ancient light, especially through its primary near-infrared camera, an instrument developed under the guidance of the University of Arizona. It senses wavelengths slightly beyond what human eyes can perceive, spanning a range where what we call visible becomes heat-dominated radiation. To achieve the extraordinary sensitivity needed to detect the weakest cosmic whispers, its sensors are cooled to just above absolute zero, nearly eliminating thermal noise. When Webb focused on an observational region known as the JADES Fields, an area carefully scrutinized through repeated and extremely long exposures, astronomers identified what seemed like a tiny red pinpoint. Its conspicuous redness instantly implied an extreme distance. All the bluer light had been stretched away, leaving only the deepest infrared channels detectable. A spectroscopic analysis confirmed this interpretation, because instead of merely recording a dot of light, the instrument spread the incoming signal into a rainbow-like spectrum. That dispersion revealed a crucial fingerprint called the Lyman break, a feature caused by hydrogen atoms absorbing ultraviolet light at a very specific wavelength. The galaxy emitted that light when the universe was staggeringly young, about 2% of its current age, and cosmic expansion inflated the wavelength enormously by the time it arrived. Yet the greater surprise came from Webb's mid-infrared instrument, which examines even longer wavelengths between 5 and 28 microns. In that regime, oxygen atoms, if present, should emit light that would also be stretched into measurable regions of the spectrum. Against all expectations, a bright oxygen emission line appeared sharply at a redshifted position, proving that the galaxy contains significant amounts of this heavier element. The signal was not faint, ambiguous, or buried in statistical uncertainty. It blazed clear and undeniable, leaving no room for second-guessing the analysis. Capturing such a result required extraordinary dedication. More than 200 hours of invaluable telescope time concentrated on a patch of sky so tiny that if held at arm's length, it would be smaller than a grain of sand. Only the most scientifically promising and distant objects ever receive this kind of commitment. Fortune also played a role. Had the target galaxy been even slightly misaligned relative to the instruments, the mid-infrared view might have missed it entirely, postponing discovery indefinitely. This combination of meticulous planning and pure chance granted humanity a rare look into the universe's youth. The existence of this detection highlights what was once impossible. Decades ago, no telescope operating in visible light, such as Hubble, could have observed such a remote and ancient system because its light has shifted far beyond visible wavelengths. Webb's infrared-focused design unlocks a window into cosmic dawn, a time when the first galaxies were only beginning to take shape. Yet what Webb revealed disrupted scientific expectations rather than confirming them. This galaxy appears far too luminous for its epoch. In theory, objects existing so soon after the Big Bang should be incredibly dim, barely visible, even through humanity's most advanced instruments. Instead, this one shines unexpectedly strong, almost defying the universe's own timeline. Observations indicate a brightness level that modern astrophysics struggles to justify. Luminous output depends heavily on how many massive stars a galaxy contains, because a star with 100 times the mass of our Sun can radiate with the brightness of 1,000,000 smaller stars combined. If this galaxy is packed with such giants, that could explain part of its intensity, but forming so many enormous stars so early challenges our standard understanding of stellar birth. Another possibility is star formation efficiency. Perhaps this system somehow transformed an unusually high fraction of its available gas into stars in a short time, achieving a level of productivity rarely seen even in later cosmic eras. Yet this idea runs contrary to theoretical predictions suggesting that early cosmic gas should have been difficult to cool and condense. Alternatively, a rapidly growing black hole might be lurking in the galaxy's center, unleashing prodigious energy as it feeds. But that introduces its own puzzle. How could a massive black hole evolve so quickly? Measurements from independent teams have repeatedly confirmed the galaxy's brightness, using multiple infrared filters and rigorous spectroscopic crosschecks, eliminating the possibility that the observation is merely a trick of dust or distance. In every test, the galaxy's luminosity remains remarkably high, The result leaves cosmologists facing uncomfortable questions. Why do the earliest visible galaxies look too advanced? How did they assemble so many stars, generate metals like oxygen, and shine with such intensity before the universe had sufficient time to allow it? Each answer appears to demand new physics or a major refinement of our cosmic story. The light from this single red dot from a realm, billions of light years away and billions of years in the past, now forces scientists to reconsider how quickly the first galaxies could ignite and evolve. It is a beacon not only across space but across our own understanding, challenging assumptions that once seemed unshakable. The notion that such a radiant, chemically evolved galaxy already existed so early in history seems to violate the universe's own age-based restrictions. How could something so complex form when cosmic time had barely begun? To illustrate the absurdity, scientists often use a playful analogy: compress the entire 13.8 billion-year history of the cosmos into a single calendar year. In that scale, this galaxy would appear as early as January 7th, at a moment when only the simplest ingredients, hydrogen and helium, should have been available. Oxygen, the substance burning brightly in this newly observed system, can only arise when enormous stars fuse lighter elements together and subsequently explode as supernovae, seeding surrounding gas clouds with their enriched ash. This cycle is not fast. It typically demands multiple generations of stars, each living and dying across stretches of millions of years. And yet, the Webb data show abundant oxygen already dispersed throughout this distant system, implying the galaxy not only birthed stars shockingly early, but repeated the cycle several times with astonishing speed. The discovery took place in a seemingly ordinary patch of the constellation Fornax, where astronomers were expecting to catalogue faint, primitive objects. Instead, Webb stumbled upon a true anomaly, a system bursting with bright, enriched starlight, catalogued officially with a long alphanumeric identifier, but more casually known among scientists as the record breaker. It lies approximately 13.4 billion light-years away, which places its formation within the universe's first few 100 million years. Every established model of cosmic evolution predicts that galaxies at this age should be tiny, dim, and composed almost entirely of primordial material. This one contradicts all three expectations at once. Its brightness is startlingly high. Its physical size stretches across an impressive span something like 1/600 light-years, suggesting it is not a compact infant system, but one that has already grown significantly. And most surprising, oxygen is present everywhere the data allow us to inspect, meaning chemical evolution progressed far more rapidly than theory permits. Stellar physics enforces unavoidable clocks. Massive stars burn fast and die young, but even the shortest lived among them require millions of years to form, fuse elements, and collapse spectacularly. Then more time is necessary for that stellar debris to spread far enough to seed gas clouds where new stars can arise. When researchers examined the observed oxygen levels and tried to work backward logically, they inferred something startling. Star formation must have begun extremely early, possibly around 200 million years after the Big Bang, essentially the moment when dark matter halos had barely begun pulling gas together. The universe had scarcely cooled. Matter had barely settled enough to clump when this galaxy already embarked on furious construction. The stunning evidence prompted independent scientific teams to repeat the measurements using different technologies. Webb's near-infrared camera delivered the first clues. Then the mid-infrared instrument detected firm oxygen spectral lines. Later, the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, confirmed the same chemical signal at radio wavelengths with breathtaking precision. A perfect agreement emerged from completely different instruments, methods, and physical regimes, removing any doubt that this observation reflects reality, not illusion. Indeed, this discovery creates a profound tension between theory and evidence. The timeline implied is brutally tight. The universe simply should not allow so much activity in such a small window. Gravity needs time to gather diffuse gas. Stars require time to ignite. Heavy elements need time to accumulate. Yet this galaxy seems to have compressed cosmic evolution into an impossible schedule. The traditional picture of galaxy growth involves a gradual hierarchical process. First, small clumps of matter form and begin creating stars. Over billions of years they collide and merge, assembling the large spirals and ellipticals we see today. But Webb now shows that sizable stellar systems arose far sooner than our simulations predict. The physics that should slow them down, supernova shock waves blowing gas away, ultraviolet radiation heating the surroundings, the challenge of cooling primordial gas, appears to have been bypassed or overwhelmed. Perhaps the first stars were even more massive than assumed, with lifetimes so short that multiple enrichment cycles played out incredibly quickly. Or maybe numerous starbursts occurred simultaneously within dense pockets of gas, rapidly building both luminosity and heavy elements. Some researchers even speculate whether exotic physics might be involved, different behavior of dark matter, unexpected cooling pathways, or black hole-driven mechanisms we do not yet understand. No matter the solution, the problem remains urgent. The existence of this galaxy forces cosmologists to ask whether the standard model of galaxy formation is incomplete, or simply missing a major ingredient. Each new observation from Webb reinforces the message. The early universe was far busier than we imagined. That realization invites both excitement and discomfort, because every data point like this demands a revision of our narratives about how order emerged from the primordial chaos. In this case, time itself has become the central antagonist. The clock between the Big Bang and the birth of oxygen-rich galaxies appears too short, unless our understanding of the cosmos is ready for another dramatic evolution. For now, this single brilliant speck from the distant past has already begun rewriting textbooks, reminding scientists that the universe still holds secrets large enough to shake the foundations of what we think we know. The process that enriches galaxies with heavy elements like oxygen is anything but gentle. When a massive star reaches the end of its short, intense life, it detonates as a supernova, an explosion so powerful that it tears the star apart and launches its interior layers outward at immense speeds. These violent shock waves heat surrounding gas to extreme temperatures, causing it to glow strongly in different parts of the electromagnetic spectrum, including X-rays and optical light. Astronomers often study nearby supernova remnants to understand this process in detail. One famous example is Cassiopeia A in our own Milky Way. There, we see twisted structures and chaotic knots of debris sculpted by hydrodynamic instabilities as the shock front expands. Some clumps of material travel much farther than others, punching outward like jagged fingers. These dense fragments remain chemically distinct, containing high concentrations of oxygen or other heavy elements forged in the star's core. Even thousands of years after the explosion, patches of stellar debris still maintain their unique chemical identity. The mixing takes time, and that slow blending becomes crucial in shaping the evolution of a young galaxy. In the earliest generations of galaxies, these enrichment events played out under different conditions than they do today. The first galactic structures were tiny by comparison, with dense reservoirs of gas crammed into relatively compact dark matter halos. In such an environment, a single supernova could influence a vast portion of the galaxy's entire gas supply. Rather than enriching just a local neighborhood, the expanding blast wave might sweep through nearly everything, rapidly transforming a chemically pristine system into one threaded with the first metals. This high-efficiency enrichment accelerated chemical evolution far more quickly than we observe in the modern universe. But this efficiency also came with a dangerous trade-off. If the explosion energy exceeded the gravitational pull of the young galaxy's dark matter halo, the gas could be blasted completely out into intergalactic space. That would effectively shut down star formation, leaving the system to stagnate. Galactic survival in these early times depended on a delicate balance. The system needed to be massive enough to keep its gas despite repeated supernova strikes. Only halos with sufficient gravitational strength could endure multiple enrichment cycles, while continuing to form new generations of stars. When numerous massive stars formed together in clustered bursts, a scenario common in the early universe, they died within a similar time frame. Dozens of overlapping supernovae would merge their shock waves into gigantic superbubbles of sizzling hot plasma that could burst through the galaxy's boundaries, driving outflows into the surrounding cosmic medium. This runaway feedback could regulate or even pause star formation temporarily. Despite that chaos, the dispersion of elements like oxygen continued. The speed of the ejected material played a key role. Travelling at thousands of kilometers per second, the debris could cross a light year in roughly a century. But even at those incredible initial velocities, spreading across a galaxy thousands of light-years wide still required tens of thousands of years just to traverse the distance. Uniform mixing took even longer. Turbulence stirred the interstellar gas like a cosmic blender. Shock waves wrinkled and folded the expanding fronts. Rotational shearing stretched clumps into filaments. Small-scale vortices shredded larger fragments. Over time, this relentless stirring gradually smoothed out sharp chemical variations. Yet complete homogenization remained elusive. Pockets of metal-rich and metal-poor gas coexisted for extraordinarily long timescales. Observations of mature galaxies today reveal that chemical unevenness persists even after billions of years of recycling and starbirth. Young stars inherit the metallicity of their birth clouds, meaning that each region within a galaxy carries the signature of its enrichment history. The oxygen-rich nature of the distant Webb galaxy indicates that many such explosive events must have occurred rapidly and repeatedly. Its observed metallicity demands not just one but multiple generations of star formation within the first few 100 million years. Every supernova contributed its load of heavy elements to the growing mix. The cumulative result produced the spectrum that Webb captured, a clear chemical imprint etched into the fabric of the infant cosmos. Under any conventional timeline, the required number of stellar generations should have taken far longer to accumulate. Yet here the evidence stands. In a galaxy so young that the universe itself had hardly matured beyond infancy, we already see the aftermath of numerous cycles of creation and destruction. Stars must have ignited soon after the Big Bang, lived short, brilliant lives, and died explosively over and over again, each generation building the chemical foundation needed for future complexity. This single galaxy therefore encapsulates a profound paradox. We witness the fingerprints of time-consuming processes in an era when very little time had passed. Heavy elements scattered throughout the system tell a story of rapid evolution that should have been impossible. But the cosmos does not lie. The photons reaching our telescopes carry the truth of what happened. What remains is the challenge to explain how it was permissible under the laws of nature we thought we understood. The early universe appears more inventive, more dynamic, and more mature than expected. Instead of a slow dawn, creation ignited quickly and fiercely, pushing the limits of our scientific imagination. One of the strongest pillars supporting this discovery is the extraordinary level of precision with which astronomers determine the galaxy's distance. Very few objects anywhere in the universe have such an exact redshift measurement. Independent scientific teams using multiple state-of-the-art observatories operating at entirely different wavelengths all reach the same conclusion. This galaxy truly lies at the extreme edge of cosmic visibility. It resides exactly where the analysis places it. 13.4 billion light-years away, shining at a time when the universe itself was still in its raw developmental stage. Likewise, the amount of oxygen detected is not an interpretation or guess, but a firmly anchored measurement, consistent across all instruments. With such a convergence of data, skepticism has little room to stand. ALMA's role in this story extends far beyond a simple confirmation. That observatory, the world's most advanced radio interferometer, has begun assembling comprehensive surveys of galaxies at comparably high redshifts. These systematic studies will ultimately reveal whether this object is an extraordinary outlier or merely the first member of a large, previously unseen population. If many galaxies at this epoch exhibit similarly elevated levels of heavy elements, then current theories face a profound and widespread crisis. If, however, this galaxy is unique, its existence must be explained by very specific, perhaps unusual circumstances. Either outcome reshapes cosmology, a new rule to rewrite, or a fascinating exception demanding special attention. Radio telescopes and infrared telescopes reveal different signatures of galactic behavior, and bringing their findings together produces a richer, multi-dimensional understanding. Each wavelength domain spotlights different physical processes, star-forming gas glowing at infrared wavelengths, molecules and fine structure emissions revealing themselves in radio frequencies. Studying the same object through both windows allows scientists to see the unseen like two eyes, creating depth perception. And so this single galaxy stands before us as a rare, exquisite example of the universe under a magnifying glass, its properties mapped with remarkable clarity across the electromagnetic spectrum. precision matters tremendously in cosmology. A small error in a galaxy's redshift becomes a massive mistake in its inferred age or distance. For nearby galaxies, such uncertainties hardly cause concern, but at the outermost edge of observation, where tiny differences translate into millions of years, accuracy becomes everything. ALMA's detection of the oxygen emission line allowed a measurement of redshift so precise that the uncertainty in cosmic timing is only around 1 million years in a universe nearly 14 billion years old. That is equivalent to identifying a single second correctly in more than 400 years of time. This extraordinary accuracy comes from the sharpness of spectral lines. While atoms within a galaxy jostle and move, slightly broadening the emitted wavelengths, the central location of that spectral feature can still be pinpointed with incredible exactness by modern radio receivers. The gas motion within the galaxy evident through a modest line width corresponding to velocities of about 200 km per second is tiny compared with the massive redshift caused by the expansion of space itself. As a result, the line peak can be extracted with extremely low uncertainty. ALMA's finely tuned systems push technological boundaries to measure wavelength shifts at precisions of 1 part in millions. Advanced calibration, powerful correlators, and meticulously characterized instrumentation guarantee trustworthy data. Such accuracy was previously unattainable for objects so far away. Earlier attempts to estimate distances relied on photometric techniques, analyzing brightness in broad filters and comparing colors to predicted models. Those methods often carried uncertainties of several percent. At a redshift of about 14, that equates to tens of millions of years of age ambiguity. Now, spectroscopy breaking light into its exact wavelengths has slashed that uncertainty by more than 1,000-fold. With this breakthrough, astronomers can place the galaxy precisely on the cosmic calendar. They know exactly when it existed, exactly how old the universe was at the time, and exactly how early in history complex chemical evolution must have already taken place. That level of certainty turns what could have been a speculative debate into a firm and undeniable revision of our cosmic timeline. The more sharply the numbers come into focus, the more astonishing the results appear. This distant galaxy is not an illusion created by misjudged distance or misunderstood brightness. It is genuinely ancient, unquestionably enriched, and undeniably bright. Every scientific tool brought to bear has confirmed its reality, and that reliability is precisely what makes the discovery so disruptive. If the evidence came from only one telescope, one method, or one wavelength, researchers might hesitate to challenge long-standing theories. But here, every independent approach reinforces the same message. Galaxies in the early universe grew faster, became chemically complex earlier, and shined far more intensely than our current understanding permits. Each new confirmation adds weight to a conclusion that can no longer be ignored. In the grand narrative of the cosmos, this galaxy is a loud contradiction shouting across 13 billion years. The universe built itself far more aggressively in its youth than we ever believed possible. The discovery forces us to rethink the entire framework through which galaxy formation has been understood for decades. Our most trusted computer simulations, refined and validated by countless observations of the present-day universe, all predict a very different picture of the cosmos at such an early stage. In the standard model of structure formation, the universe begins with tiny fluctuations in density, small ripples imprinted into space-time during the inflationary moment just after the Big Bang. Over time, these overdense patches attract matter through gravity, gradually collapsing into dark matter halos. Ordinary hydrogen and helium gas fall into these gravitational wells, eventually cooling enough to form the first stars. According to this long-held view, small protogalaxies merge together over billions of years, stacking complexity layer by layer like bricks forming a skyscraper. Simulations faithfully reproduce a wide range of modern galactic properties: the way galaxies cluster, the rotational behavior of spirals, the diversity of galaxy shapes, and the overall history of star formation across cosmic time. Because of this success, confidence in the theoretical framework has remained steadfast until now. When these same models are pushed back to the earliest cosmic dawn, they fail in multiple critical ways. At a redshift of around 14, models predict that the most massive dark matter halos available should hold only a modest amount of baryonic matter, far less gas than is necessary to create a large, bright galaxy. Even converting all that primordial gas directly into stars which would itself violate physical constraints would still fall short of the stellar mass indicated by observations. There simply is not enough material, nor enough time to transform it into starlight at the scale we now see. Some theorists have suggested boosting star formation efficiency in simulations to the highest allowable limits, imagining that the earliest galaxies converted gas into stars much more effectively than their modern descendants. However, this adjustment introduces another inconsistency. Feedback from those newly formed stars would have been even harsher in the early universe. Massive stars flood their surroundings with intense radiation and erupt as supernovae only a few million years later. These processes heat and expel gas, making it harder, not easier, for future stars to form. It becomes a self-defeating cycle. The more vigorously a galaxy forms stars, the stronger the suppression that follows. The timeline for chemical enrichment poses a second and equally severe challenge. Even if the very first generation of stars formed rapidly and exclusively as massive giants, an idea many models already incorporate, there still are not enough cycles of birth and death available to account for the oxygen abundance recorded by Webb. Each generation of stars takes time to form, live, and die, and the debris from those supernovae take time to mix thoroughly into surrounding gas. These steps require tens of millions of years per generation under the most optimistic assumptions. To have gone through several cycles by 300 million years after the Big Bang pushes physical plausibility to its breaking point. With every attempt to force the models into compliance, another contradiction appears. If early galaxies formed stars too quickly, they should have destroyed or expelled their gas entirely. If they formed stars slowly, they would remain chemically primitive and dim. The observed galaxy manages to be both metal-rich and brilliantly luminous, an outcome the standard theory deems nearly impossible. To reconcile this tension, some researchers propose more radical ideas. Perhaps dark matter behaved differently in the early universe, allowing halos to form sooner or grow faster than current models predict. Perhaps gas could cool through unexpected mechanisms, collapsing into stars without waiting for heavy elements to develop as catalysts. Or maybe supermassive black holes formed astonishingly early and influenced the growth of galaxies in ways we do not yet fully grasp. Any of these ideas would constitute a substantial revision to the physics that underlies our cosmological models. Meanwhile, simulations continue to struggle. Even the most advanced high-resolution runs, including those designed specifically to test extreme early star formation scenarios, still fall short by large factors when trying to match the mass, brightness, and metallicity observed in this single ancient galaxy. Something fundamental is missing. Where theory insists on slow measured growth, observation shows rapid upheaval and dramatic transformation. The cosmos we uncover with Webb feels impatient, determined to build complexity with remarkable urgency. Instead of a quiet dawn, the early universe erupts with star factories and explosive enrichment. The conventional picture of how and when galaxies assemble, the neat hierarchy that climbs from tiny building blocks to majestic systems like the Milky Way now, seems too simple, too slow, and perhaps incomplete. The discovery demands humility. As powerful as simulations are, they remain approximations, rooted in assumptions that may require bold revision. In the coming years, increasingly sensitive surveys will reveal whether the record-breaking galaxy is a lone renegade or the first of many such anomalies. Whichever scenario proves true, one conclusion is already clear. The universe did not wait politely for billions of years to ignite its grandeur. It began crafting astonishing structures almost as soon as existence permitted. And every new glimpse into that formative era pushes scientists to reshape cosmic history into a narrative that matches the astounding reality now unfolding before our eyes. Even the most far-reaching attempts to adjust theoretical models cannot overcome the relentless hurdle of time. Every step in the life cycle of stars and galaxies consumes precious millions of years. Years that simply did not exist when this ancient system was already shining with heavy elements. Gas must first cool enough to collapse into the dense cores that initiate starbirth. That cooling process requires the gas to radiate away its energy, something primordial hydrogen and helium struggle to do efficiently without the help of heavier elements. Then the resulting stars must burn intensely before exploding as supernovae, scattering new elements outward. After that, the enriched gas must again cool, condense, and repeat the cycle so a fresh generation of stars can emerge. Models show that even under the most accelerated possible circumstances, only one or two such cycles could realistically occur by 300 million years after the universe began. And yet this galaxy contains amounts of oxygen implying numerous star-forming bursts. This mismatch between theory and observation grows more striking with every new detail astronomers extract from the data. Studies try to imagine plausible tweaks, different initial mass functions favoring enormous primordial stars or unusual environments that concentrate matter more efficiently, but even these modifications fail to produce sufficient enrichment in the short available window. It becomes increasingly difficult to explain the observations without invoking some new or unexpected factor in early cosmic evolution. Could dark matter halos in the young universe have formed faster or collapsed more efficiently than our current understanding allows? Dark matter composes the gravitational backbone upon which galaxies grow. If its behavior changed subtly in those earliest epochs, perhaps interacting in ways we have not yet detected, it might have accelerated the gathering of baryonic gas. Others propose that cooling mechanisms involving molecular hydrogen or exotic pathways may have allowed gas to reach star-forming conditions much sooner than expected. There's even speculation that the seeds of supermassive black holes emerged almost immediately after the Big Bang, injecting additional energy into galaxies and influencing how fast they developed. All these possibilities remain speculative and require careful testing, but their very consideration reveals how disruptive this discovery has become. Observations like this one have also begun to highlight a fundamental truth. The earliest universe did not evolve gently or predictably. Instead, it appears bursting with violent intensity. Star-forming regions must have been extraordinarily dense, cramming together material that ignited into short-lived giants by the hundreds or thousands. Their catastrophic deaths then supercharged the growth of chemical complexity, fueling subsequent starbursts. The young cosmos behaved like a forge running at full heat from the very beginning. Where theory predicts cautious and gradual assembly, the evidence reveals ambition and urgency. A critical part of the puzzle comes from the staggering brightness of this galaxy. Its luminosity indicates a population of stars so energetically radiant that astrophysicists must reconsider the maximum pace of early star formation. Traditional constraints assume that feedback from powerful stars regulates the rate of growth, preventing runaway expansion, but this galaxy seems to show that such regulation was far less limiting than once believed, or perhaps operated differently in primordial conditions. Some simulations suggest that early gas clouds may have remained extremely cold despite intense radiation, allowing them to fragment rapidly into numerous massive stars. If correct, this would change our understanding of the earliest stellar populations, painting a picture of cosmic neighborhoods where starbirth occurred in furious waves, each adding more light and more metals to the galactic core. Yet even these bold scenarios struggle to match the scale of enrichment observed. The oxygen detected by Webb and ALMA is not confined to a small central region, but appears widely spread throughout the galaxy, implying efficient mixing. The challenge multiplies. Not only must many stars have formed and died extremely fast, but the resulting chemical debris must have been distributed remarkably uniformly in very little time. Every piece of the puzzle demands speed faster than standard physics allows. These tensions between theory and observation hint at potential blind spots in our assumptions about how matter behaved at high redshifts. It may turn out that the first galaxies did not resemble the dwarfed protostructures commonly illustrated in textbooks. Instead, they may have formed in massive bursts, more like sudden eruptions of complexity than cautious incremental steps. That shift could influence our understanding of everything from the reionization of the universe to the growth of cosmic structure on the larger scales. For decades, scientists believed they were gradually closing in on a complete picture of galaxy formation. But with each new observation from Webb, the horizon of mystery expands again. Early cosmic history now appears far more dynamic, far more explosive, and far less forgiving to slow-building theoretical constructs. The universe in its youth was not a quiet nursery. It was a chaotic workshop fueled by relentless creation and destruction. This galaxy stands as a shining, oxygen-rich reminder. The cosmos has always been capable of surprising us, especially when we reach for its most distant and ancient chapters. The timing implied by this discovery strikes at the deepest foundations of cosmology. The universe enforces limits, Matter can collapse only so quickly, stars can evolve only so fast, and heavy elements require sequential cycles of stellar birth and destruction. Yet this one galaxy appears to have raced through that entire evolutionary ladder with reckless acceleration, finishing tasks that should have needed far more time. Observational data from Webb and ALMA leave no room to stretch the timeline. This galaxy truly existed when the cosmos was still in its dawn phase, just a few 100 million years after the Great Expansion began. That is a period when cosmic gas remained mostly neutral, and darkness still filled the intergalactic space between the very first clusters of stars. The ionization era, the grand transformation in which ultraviolet light from young galaxies stripped electrons from hydrogen across the cosmos, was only just beginning. According to standard theory, the earliest galaxies should have been too small to do much more than flicker faintly, their primitive stars barely beginning to assemble complexity. And yet, right at the edge of observability, we find a system bursting with mature chemical signatures as though cosmic evolution had sprinted ahead to a later phase. One of the biggest implications of this discovery relates to how galaxies contributed to ionization. The brightness of this system suggests an unusually high population of massive ultraviolet-emitting stars. If many galaxies like this existed, they may have been far more influential in lighting up the early universe than previously assumed. Instead of a gentle and gradual brightening, reionization might have been powered by intense stellar factories, igniting earlier than expected, altering the timeline of how the first transparent universe emerged. As scientists continue to examine the evidence, it becomes increasingly clear that the early cosmos was not a hesitant architect. It built structures rapidly, producing dense concentrations of material that could ignite brilliant starbursts in short succession. This has caused cosmologists to revisit questions long thought to be settled. What were the first stars like? How quickly did dark matter halos grow? What role did violent feedback play in shaping the earliest galaxies? Traditional models portray feedback from massive stars as a restraining force. Explosions blow gas out of fragile young halos, temporarily choking off later star formation. But perhaps the earliest environments were so densely packed that even powerful outflows could not escape easily. Instead of depriving galaxies of fuel, the turbulent aftermath of supernovae might have compressed nearby gas clouds, seeding rapid follow-up star formation rather than preventing it. If this self-reinforcing cycle occurred repeatedly, it could produce several generations of stars in short order, naturally leading to the unexpected metal abundances observed today. Still, the gap remains steep. Even the most extreme assumptions struggle to generate such widespread oxygen across the entire galaxy so quickly. Astronomers have even considered whether mergers played a hidden role. If two smaller galaxies, each having undergone their own rapid evolution, collided early in cosmic history, the combined system might suddenly appear far more evolved. Mergers are known to trigger explosive star formation in later epochs, and the early universe likely experienced chaotic interactions at an even faster pace. But once again, time works against this explanation. To merge, halos must first form, attract gas, create stars, and then interact through gravitational dance. Even rushing every step to its physical limits, there hardly seems enough room in the cosmic schedule for all this to occur by 300 million years. That kind of complexity normally unfolds over much longer intervals. The deeper scientists look, the more this galaxy emerges as a paradox, something that is not supposed to exist, yet clearly does. Spectroscopy has locked down its redshift. Photometry confirms its intense luminosity. Radio data underline its oxygen enrichment. The combined evidence demands an answer. What mechanism allowed such drastically accelerated assembly of mass and metals? Theories quickly begin bending in uncomfortable directions. Some suggest the nature of dark matter may hold the key. If dark matter interacts with itself in ways not accounted for by the standard cold dark matter model, structure could form faster in the early universe. Others propose that certain types of primordial gas clouds may have collapsed into massive stars almost instantly, bypassing slow cooling processes. There are also whispers of a more dramatic possibility, that unknown physics, active only in the earliest moments after the Big Bang, seeded the universe with the conditions needed for rapid growth that later disappeared. Whatever the explanation, this discovery proves we still lack a full understanding of how the universe transitioned from simplicity to complexity. It challenges the comforting assumption that our existing models merely need fine-tuning. Instead, it suggests that some part of our foundational picture may require genuine reimagining. Perhaps the cosmic dawn was not a slow sunrise, but a sudden blaze more rapid, more chaotic, and more efficient than any simulation has been willing to admit. The early universe, it seems, refused to wait. It leapt forward with bold ambition, crafting galaxies that shine across billions of years to confront us with mysteries we must now work to unravel. The discovery of this astonishingly evolved galaxy so soon after the universe's birth not only challenges theoretical frameworks, it also compels astronomers to broaden the scope of future observations. The James Webb Space Telescope has already demonstrated that it is capable of revealing objects far more complex than the hierarchical growth models predict for such an early epoch. Each new ultra-distant galaxy detected forces scientists to confront an unsettling possibility. Maybe this object is not a rare outlier, but merely the first instance of a widespread population we have never been able to see until now. If more galaxies like this emerge from Webb's deep surveys, it would mark a turning point in cosmology. The early universe would need to be reinterpreted as a realm where large chemically advanced structures appeared with remarkable speed, driven by mechanisms not yet accounted for. In that scenario, a massive re-evaluation of how star formation and chemical enrichment operated in primordial environments would become unavoidable. On the other hand, if this galaxy remains singular in its rapid evolution, scientists will need to uncover what extraordinary set of circumstances allowed it to leap ahead of its contemporaries. Either way, it promises years of intense investigation and theoretical creativity. Meanwhile, the data from ALMA and Webb also emphasize the importance of multi-wavelength astrophysics. Infrared observations reveal light emitted from stars and warm gas, while radio telescopes target cold molecular gas and subtle emissions from heavy elements, each probing different aspects of galactic structure and evolution. When these viewpoints align as precisely as they do for this galaxy, the results form an unshakable foundation. This synergy is not merely convenient, it is essential, especially when pushing the boundaries of what can be detected at cosmic extremes. It is through this collaboration between observatories that scientists gained access to such incredible precision in redshift measurement, enabling them to pinpoint the galaxy's epoch within a narrow million-year window. The stunning clarity of this timing means there is no safety net for outdated assumptions. The timeline must be accepted as real, and theory must adapt accordingly. This degree of confidence leaves scientific explanations with very little room to hide. For years, cosmologists have been able to fall back on uncertainties when observations seem to stretch the limits of possibility. But here, multiple independent datasets agree without wiggle room. The galaxy exists where it should not. Therefore, our understanding of that era must evolve. As troubling as this may be for established theory, it also presents an exhilarating moment for discovery. Cosmology thrives on tension between expectation and reality. When observations contradict predictions, it is not a sign that science is failing, but rather a sign that science is advancing. Such contradictions illuminate the gaps in our knowledge that must be explored to move forward. And in the history of astronomy, breakthroughs often follow moments like this when the universe refuses to match human expectations. The theoretical discrepancies extend into another major aspect of early galactic evolution: how quickly galaxies can gather mass. In the well-tested hierarchical model, galaxies grow primarily through mergers, steadily accumulating greater amounts of gas and stars as gravity pulls smaller systems together. But this scenario demands extensive time to play out. Collisions and mergers do not happen instantly. They require coordinated movements across vast cosmic distances. For a galaxy to reach such substantial size while still immersed in the universe's infancy implies either exceptionally rapid dark matter, halo growth, or an entirely different formation pathway. This has led some researchers to propose that the seeds of this galaxy might have originated before the conventional timeline of structure formation even began. Perhaps certain regions of the early universe collapsed faster, due to local variations in density far higher than standard models allow. These densest pockets, born from primordial quantum fluctuations, could have acted as shortcuts in the cosmic construction process. Gas would have gathered quickly, stars would have formed in intense bursts, and metals would have blossomed sooner than anticipated. The result: galaxies like this one appearing out of schedule, as though handed a cosmic head start. Yet for such a scenario to be true, simulations would need to incorporate more extreme initial conditions than currently used, suggesting the early universe was more chaotic and uneven than typically illustrated. And if these denser-than-expected regions were common, rather than rare flukes, our entire conception of how galaxies populate the universe must change. Webb is now at the vanguard of determining which view reflects reality. As more deep-field images come online, and more candidates from the cosmic dawn receive spectroscopic confirmation, scientists expect a clearer pattern to emerge. But already it is becoming harder to defend the once comfortable assumption that the early universe was slow to evolve. The rapid rise of brightness, mass, and metal content in this galaxy forces a re-evaluation of what early truly means in cosmic development. Perhaps the transformation from simplicity to complexity was not a gradual slope, but a steep climb undertaken almost immediately after the universe became transparent. That perspective reshapes the entire story of how the universe built the diversity we see today. No longer does evolution unfold as a lazy drift from darkness into light. Instead, it appears the cosmos ignited at full speed, producing galaxies that defy the very rules we believed governed the young universe. Every photon captured from this extraordinary system demands that cosmology embrace a more dynamic past. And those demands will only grow louder as Webb continues its journey deeper into time. As astronomers confront the implications of this astonishing galaxy, another aspect of the discovery gains importance: the direct measurement of its gas dynamics. The width of the oxygen emission line within the spectrum reveals how fast gas clouds inside the galaxy are moving relative to one another. These internal motions provide a clue to the overall mass and gravitational structure of the system. In this case, the velocity dispersion is measured at around 200 km per second, a value far from trivial. For context, such internal speeds suggest a gravitationally bound object of significant mass, yet again contradicting the idea that galaxies of this era should be extremely small and fragile. While the expansion of space generates the primary redshift that shifts the spectrum to longer wavelengths, the subtle broadening of the line arises from the motion of the gas itself, like the Doppler effect heard in the changing pitch of a passing siren. This measurement allows astrophysicists to infer not just the galaxy's age and composition, but its internal structure and maturity. The dynamical properties suggest that this galaxy has had time to develop a relatively organized gravitational system, yet time is exactly what this early epoch should lack. It is as though the universe skipped steps, fast-forwarding past the slow assembly phase that theory insists must occur. This again raises a central question. Are our assumptions about the earliest dark matter halos incomplete? According to the standard cosmological framework, the dark matter halos forming around 300 million years after the Big Bang should be too small to anchor such high velocities without losing their gas to the violent feedback of supernova explosions. Gas moving at 200 km per second should be able to escape a primitive halo, leaving behind a ghostly remnant incapable of building further generations of stars. Yet here we see a system that has retained its enriched material long enough to form a diverse stellar population. Somehow, gravity in this environment was strong enough to keep everything bound together. This hints that either the halo is far more massive than expected for its era, or dark matter operated with greater efficiency in the young cosmos, perhaps clumping into deeper wells earlier than predicted. Such implications ripple outward into the broader field of cosmology. If early structures were indeed more massive that would impact the timeline of cosmic reionization, the distribution of matter in the observable universe, and even the interpretation of data from the cosmic microwave background. Every pillar of the lambda CDM model, the reigning cosmological framework, relies on precise timing. When one part moves faster, the entire structure must shift to accommodate it. Moreover, the precision of the distance measurement greatly limits alternative explanations. In previous decades, when astronomers encountered faint red objects with unusual properties, they could often attribute them to misidentified redshifts or gravitational lensing that artificially amplified brightness. But none of those escape routes apply here. Multiple independent methods converge to the same redshift value, pinning the galaxy firmly in the earliest observable era. Its unusual brightness, size, and metal content cannot be dismissed as observational illusions. It is truly sitting at the frontier of the known universe, shining defiantly through the fog of cosmic infancy. Every parameter that could have weakened the case distance mass composition has instead sharpened it. Time and evidence are cornering theorists into a corner from which retreat is no longer an option. For years, the scientific community anticipated that Webb might reveal some early surprises, perhaps a population of small galaxies slightly more evolved than anticipated. But no one expected a system this large, this bright, and this chemically advanced to appear so soon after the Big Bang. With each measurement confirming its properties more securely, the shock becomes more profound. Astronomers now find themselves asking, if this galaxy exists at this time, how many more like it remain hidden, waiting for detection? Have our instruments until now simply been too limited to see what was always there? And if so, how drastically must we revise our ideas about what the early universe looked like? This revelation challenges the deeply held view that cosmic structure built itself up carefully, through successive mergers over billions of years. Instead, the universe may have jumped headlong into the era of galactic engineering, constructing luminous giants, while cosmic radiation still echoed from the primordial explosion. If true, then the story of creation is less a gradual nurturing of starlight, and more a roaring ignition, a cosmic furnace roaring to life almost immediately. The gas motions within this galaxy expose that bold nature clearly. They reveal a system powerful enough to resist being blown apart, cohesive enough to maintain enriched gas, and productive enough to host multiple stellar generations. It defies expectations not in one area, but in every measurable way. And its very existence insists on a fundamental truth. The early universe was not a realm of timid beginnings. It was a landscape of aggressive creation, where physical processes operated on fast-forward, turning simple gas into complex galactic ecosystems in a geological heartbeat. As we continue to peel back the layers of the cosmos, discoveries like this illuminate an undeniable reality. The universe holds far more mysteries than we once dared to imagine, and it has only just begun to reveal them. The tension between what we observe and what we predict grows sharper with every advance in measurement. This galaxy's precise placement on the cosmic timeline reveals just how radical its existence truly is. When we say it appears only 300 million years after the Big Bang, that number may seem large on a human scale. But in cosmic terms, it is the blink of an eye, barely enough time for the universe to expand, cool, and allow gravity to gather the first gas clouds. For this system to become so large, so luminous, and so chemically enriched within that narrow window means that the earliest galaxies kicked into high gear almost immediately. They were not hesitant pioneers feeling their way through the dark. They were roaring engines of creation. To put this into perspective, astrophysicists often compress the history of the cosmos into a single year, with the Big Bang at midnight on January 1st and the present moment at the following December 31. In that analogy, Earth would form on September 1st. Dinosaurs would roam in late December, and human civilization would occupy only the final seconds before the year ends. Within that same framework, this galaxy would appear within the first week of January, at a time when the cosmic story had barely begun, long before any chemical elements other than hydrogen and helium should have existed. Yet here it stands, burning bright with oxygen, a product of multiple generations of short-lived massive stars. The implication is astonishing. The universe wasted no time at all. From the moment conditions allowed matter to clump, stars lit up and began forging heavier elements at a pace that modern physics struggles to justify. Understanding how this happened becomes one of the most urgent questions in cosmology. Theoretical models assume that star formation efficiency in the early universe was low due to fierce radiation and explosive feedback from the very first gigantic stars. These forces should have prevented gas from cooling quickly enough to form subsequent generations. But instead of halting growth, it now appears that this energetic feedback may have acted as a catalyst, cramming and compressing the surrounding medium into new bursts of starbirth. Rather than throttling evolution, chaos may have served as the universe's accelerator. Another key factor is the distribution of heavy elements observed throughout this galaxy. Metals like oxygen are not produced evenly. They originate deep within a star's core, then must be scattered by supernovae and mixed throughout the galactic gas reservoir. In today's galaxies, complete mixing takes great spans of time and often remains incomplete after billions of years. Yet in this distant object, oxygen already appears widespread, implying both rapid enrichment and rapid homogenization. Turbulent flows, high densities, and repeated energetic events might have stirred the gas efficiently enough to erase signs of chemical youth. The result? A galaxy that looks far more mature than its cosmic age should allow. The consequences of this rapid evolution extend beyond the galaxy itself. Heavy elements play a crucial role in cooling gas clouds. The more metals present, the faster gas cools, the more efficiently stars form. This means that once enrichment begins, it creates a positive feedback loop, accelerating growth even further. It is possible that this galaxy benefited from such an early and aggressive boost, giving it a head start on becoming a star formation powerhouse. If that is correct, then early galaxies may not have been the dim embryos we assumed, but instead luminous hubs that helped reionize the universe far earlier and more effectively. Yet these explanations still wrestle with the ultimate constraint: time. Too many cycles must occur in too few millions of years, and every observational result tightens the limits. The galaxy shines brightly enough that it must contain large numbers of massive stars. It shows a level of chemical maturity requiring extensive recycling of matter. It retains fast-moving gas that demonstrates a robust gravitational, all indicators of a system much farther along in its development than theory currently permits. Even if gas collapsed instantly and star formation operated near maximum possible efficiency, the numbers struggle to align. The timeline seems cruelly short, almost mocking our attempts to rationalize the situation within standard frameworks. This is where cosmology faces a crossroads. Either the scenarios used in current simulations are missing crucial physics, or the boundary conditions applied to early universe modeling must be rewritten entirely. Perhaps the cosmic dawn was shaped by physical laws that behave differently under extreme conditions, laws that only reveal themselves at the furthest reach of time and distance. It may take years of research, dozens more discoveries, and countless refinements to our theories before we can fully comprehend what this one galaxy is trying to tell us. But its message is already loud and clear. The universe did not grow in modest increments from simplicity into complexity. Instead, it experienced an explosive leap forward, an era of wild creativity that, until recently, lay hidden from our view. Now that Webb has opened this window, we cannot close it. The cosmos is showing us its true pace at the beginning, fast, fierce, and far more inventive than we ever imagined. As researchers dig deeper into the scientific implications of this ancient galaxy, another crucial aspect emerges. Its intense luminosity reveals a staggering rate of star formation, one that pushes the boundaries of what is physically plausible. The amount of starlight pouring from this system suggests that its young stars are forming in massive clusters, each containing hot, short-lived giants, capable of producing fierce radiation and powerful stellar winds. These conditions, while hostile and turbulent, are exactly what is needed to enrich a galaxy with heavy elements on a rapid timetable. But they also raise a paradox. How does such widespread and tumultuous activity sustain itself long enough to build a galaxy of this scale? In typical scenarios, when too many massive stars form at once, their explosive deaths rip apart the surrounding gas, temporarily halting future star birth. Yet this galaxy appears not to have succumbed to such destructive cycles. Instead, it shows every sign of persistent growth, as if the early universe provided a unique environment where destructive forces were somehow converted into creative ones. Perhaps the density of matter was so high in those primordial times that even powerful blasts from supernovae remained confined, merely stirring gas into new waves of collapse, rather than flinging it into the void. Or maybe the dark matter halo anchoring the galaxy was already extraordinarily massive, imposing a deep gravitational grip strong enough to retain nearly all expelled material. This would allow the cycling of star formation to proceed continuously, like a furnace that refuels itself. Such a scenario would transform early galaxies into cosmic engines, forging metals and amplifying their own growth at a breakneck pace. Another intriguing consequence of this discovery is its impact on the long-running debate about the first stars, known as population 3 stars. These stars, composed of nothing but hydrogen and helium, are believed to have been colossal, hundreds of times more massive than the Sun, and to have lived incredibly short lives before exploding into brilliant supernovae. For years, astronomers have searched for definitive evidence of these primordial giants through the imprint of their chemical signatures. While this galaxy does not show the untouched purity associated with population 3 stars, its elevated oxygen levels imply that such massive early stars did exist and were able to transform their surroundings with astonishing speed. If this system went through multiple rapid cycles of star formation involving such monsters, then it may represent one of the first galaxies to emerge from the primordial era of pristine stars into a chemically enriched universe. It stands as a boundary marker, a signpost indicating the moment when the cosmos began shifting from simplicity to complexity. The presence of heavy elements also influences how stars form and how galaxies develop their structure. Metals allow gas to radiate away heat more efficiently, causing star-forming clouds to fragment into smaller pieces and give birth to more moderate-sized stars. This means that by the time we see this galaxy, the initial phase dominated by supermassive primordial stars is already transitioning to a more balanced cosmic environment. The universe appears to have entered a phase of rapid chemical maturation almost immediately. The question then is not simply how one galaxy evolved so quickly, but whether this behavior was common among the earlier systems. If rapid enrichment and aggressive star formation were typical rather than exceptional, then the entire sequence of cosmic history must be reconsidered. The first billion years may have been far more densely packed with transformative processes than previously believed. As a result, astronomers now look toward future surveys with Webb, ALMA, and upcoming observatories to uncover more examples. Should dozens or hundreds of similarly evolved galaxies be found at comparable distances, a major paradigm shift will become unavoidable, and even if this galaxy proves rare, it must be explained as a feature allowed by the universe, not dismissed as an anomaly to be ignored. Rare events can still reshape our theories when they reveal a possibility that models fail to produce. The shock waves from this discovery ripple out into nearly every field of astrophysical research. Cosmologists must rethink how dark matter halos grow. Theorists must revisit assumptions about gas cooling and feedback. Chemical evolution models must be revised to allow metals to appear almost instantaneously. Even the role of black holes at the dawn of cosmic time may need re-examination. Could young galaxies like this one have been hastened by early massive black hole seeds that heated and stirred gas more productively than expected? For now, every explanation remains provisional. Scientists are left with a sense of awe and a sense of urgency. Awe, because the universe continues to reveal grander ambitions than we dared predict. Urgency, because Webb has shown us there are deep cracks in what we thought was settled knowledge. This galaxy is a reminder that our understanding of cosmic history is still incomplete, and that some of the universe's most important chapters remain unwritten in our textbooks. With each new detection, the cosmos is quietly challenging us to update the story. Not a cautious evolution, but a fierce and accelerated rise into complexity. And as more data flow in, we may find that the universe was always more innovative in its earliest moments than any of us imagined. Beyond the theoretical puzzles, this discovery has become a powerful demonstration of how transformative the James Webb Space Telescope truly is. For decades, astronomers dreamed of witnessing the universe in its infancy, not through inference, but through direct observation of the very first galaxies assembling their stars, sculpting structure out of formless gas. Previous telescopes could only scratch the surface, detecting faint smudges of light without the clarity needed to decode their internal properties. With Webb's enormous mirror and infrared vision, those limitations have finally been shattered. This galaxy, blazing forth from the cosmic dawn, is exactly the kind of revelation the mission was built to uncover. It proves that the early universe was filled with processes that remained invisible until the right technological tools were available to reveal them. And by pushing into this unexplored frontier, Webb has not only expanded our view, it has overturned long-standing assumptions about the pace and nature of cosmic evolution. What once seemed mythic speculation has now become measurable reality. As Webb continues to survey deeper fields and search for even earlier structures, it will build a growing statistical sample. Perhaps dozens of galaxies with similarly rapid enrichment will emerge. If that happens, scientists will no longer be debating the existence of such systems. They will be tasked with explaining why the universe so consistently produced them. A revised picture of early cosmic history may take shape, one in which rapid growth and chemical sophistication were not astonishing exceptions, but major defining features of the first few 100 million years. But even if this particular galaxy stands alone as one of the universe's earliest and most extreme overachievers, it still sends an unmistakable message. It demonstrates that the cosmos at times leaps forward, rather than proceeding with steady caution. In doing so, it reminds us that reality frequently outpaces theory. Astrophysics has a distinguished history of adapting to discoveries that initially appeared impossible, from quasars to pulsars to the accelerating expansion of the universe. Each time, the revelation did not break science. It strengthened it by forcing deeper inquiry. The same will be true here. Researchers are already refining computational models to incorporate more aggressive pathways for rapid star formation and metal dispersal. Simulations are being updated to test how feedback might behave differently under extreme early universe densities. Some even explore the idea that dark matter physics could vary subtly across time, altering the rate at which halos grow in the cosmic dawn. While none of these revised models have yet achieved full agreement with the observations, the gap is narrowing proof of how quickly the scientific process adapts to new challenges. Meanwhile, observational campaigns will expand into multiple directions. Longer exposures and gravitational lensing could reveal even fainter galaxies at similar redshifts, producing a clearer picture of the population distribution. Spectroscopic surveys will look for variations in chemical fingerprints among early galaxies. Some may show dominance of carbon or silicon, others richer in nitrogen or magnesium, and these differences will tell stories about the earlier starbursts and the diversity of their environments. Comparisons between galaxies at slightly different ages will map how quickly chemical maturity advanced in the first few 100 million years. Combined with measurements of gas mass, size, and internal turbulence, this developing dataset will form the foundation for a significantly revised model of galactic evolution. There is also a growing curiosity about how the environment surrounding this galaxy influenced its growth. Was it born within a protocluster surrounded by a high density of neighboring halos that fed it through continuous mergers and gas inflow? Or did it occupy a privileged region of space where conditions naturally seeded faster evolution? The potential presence of a forming cluster could reveal that large-scale structure emerged much earlier than previously believed. Webb and Alma may soon explore the space around this galaxy, searching for companions whose discovery could further disrupt our cosmic timeline. Whatever the final answers may be, one truth remains constant. The universe is not following the careful script we wrote for it. Instead, it's revealing a far more dramatic origin story, one in which creativity flourished instantly after the Big Bang. Every new observation from Webb pushes open that door wider, inviting us to re-examine what is possible. The search for the first galaxies was once a quest for faint sparks igniting the night. Now, unexpectedly, we find blazing furnaces already at work when cosmic time itself was still scarcely underway. And this realization forces a humbling acknowledgement. Our greatest assumptions about the universe's youth are not only incomplete, they may be fundamentally flawed. Yet, in that humility lies excitement. For where knowledge falters, discovery thrives. This galaxy is not merely an ancient relic, it is a message from the first chapters of existence. A message urging us to reconsider the universe, not as a slow learner, but as an audacious prodigy that mastered complexity almost immediately. Another dimension of this discovery involves the interplay between observation and interpretation, reminding scientists how essential it is to continually reassess the assumptions baked into their methods. For many years, the ability to determine the mass, age, and composition of extremely distant galaxies relied heavily on indirect techniques, such as modelling the colour of their emitted light or comparing observed brightness to theoretical templates. Those tools were the best available at the time, but they came with uncertainties that were often difficult to quantify. Webb's powerful spectroscopic instruments, however, changed the game entirely. Instead of estimating, astronomers can now directly measure the physical signatures of key elements, analysing the precise wavelengths emitted or absorbed by gas swirling inside the galaxy. These chemical fingerprints are sharp and unambiguous, revealing new truths the earlier methods struggled to uncover. With this leap in technology, surprises were almost guaranteed, but few anticipated a revelation this dramatic. As the data accumulates, the scientific community finds itself balancing healthy skepticism with mounting evidence. Astronomers carefully recheck calibration pipelines, verify the instrument's performance, and explore whether extreme gravitational lensing could artificially amplify or distort the object's properties. But each investigation returns the same verdict. The observations are robust. This galaxy's light truly began its journey when the universe was still trembling from its own creation. It is a direct witness from the time when matter first organized itself into structure, and its existence demands a new approach to understanding how physics operated under the pressures and densities of the early cosmos. This galaxy also compels a reassessment of what astronomers call the dark ages of the universe, the period after the cosmic microwave background cooled, but before the first stars illuminated space. Previously, this era was envisioned as a long, uneventful wait for gravity to build the first stellar nurseries. But if galaxies of considerable mass and luminosity were already burning passionately by 300 million years, that vision must shift. The Dark Ages may have ended far earlier than predicted. Light may have begun conquering the darkness almost immediately, driven by star factories that appeared in sudden bursts across the cosmos. This changes how we think about the reionization epoch. Traditionally, the assumption was that countless tiny galaxies gradually ionized hydrogen throughout billions of light years. But a strong population of early giants like this one could have contributed an enormous share of the necessary ultraviolet photons, accelerating the transformation. The entire picture of how the universe transitioned from opaque to transparent must now be reconsidered in light of these findings. There is also profound impact on the future of cosmological surveys. No longer can astronomers assume that early galaxies existed only as faint, low-mass protoclusters. Detection strategies must adapt to expect the unexpected. Large-scale efforts like Webb's deep fields, coordinated ALMA observations, and upcoming infrared missions will likely shift their search tactics to better capture chemically advanced systems at extreme distances. And this galaxy has set a new benchmark, a target against which future theoretical models will be judged. If a model fails to predict conditions allowing such rapid enrichment, it will be considered incomplete. Instead of fine-tuning around known outcomes, simulation frameworks must expand to encompass a broader range of possibilities, including those that once seemed improbable. This era of astronomy is not merely about finding new objects. It is about uncovering a new layer of reality governing the universe's formative years. The discovery forces scientists to adopt a more flexible view of cosmic evolution. For decades, the field has been guided by the paradigm of gradual hierarchical assembly, tiny halos merging into larger ones over extended timescales. That narrative may still hold in a general sense, but it is now evident that certain systems advance with startling speed. The early universe was not homogeneous in its pace of development. Some regions sprinted ahead while others crawled. Understanding what conditions triggered such accelerated growth, be it exceptionally dense regions, unusual dark matter behavior, or highly efficient cooling, will reshape our models of cosmic emergence. Meanwhile, the significance of this discovery resonates far beyond the technical world. It touches on a fundamental human fascination, the desire to know where complexity comes from. How did the first galaxies arise? When did the universe begin to resemble the one we inhabit today? What mechanisms allowed matter to climb from simplicity to dazzling sophistication? This galaxy offers a tantalizing clue that the rise of structure was not a slow and cautious evolution, but rather a bold experiment conducted by nature at the universe's earliest moment. Scientists and the public alike are drawn to these distant beacons because they reveal our own origins. Every atom of oxygen in our lungs was forged in ancient stars like the ones enriching this galaxy. To see heavy elements so early is to witness the very beginning of the cosmic alchemy that would ultimately lead to planets, biology, and conscious observers capable of asking these profound questions. It underscores a poignant truth. The universe was preparing the ingredients for life long before stars like our Sun existed. In this way, the discovery is not just a scientific advancement, but a philosophical one. It reminds us that creation started immediately, that from the first possible moment, the cosmos was actively building toward complexity. And if such rapid evolution was underway at a time so close to the beginning, then the story of existence may be even richer and more dramatic than we ever imagined. One of the most striking lessons from this discovery is the importance of humility when confronting the unknown. Astronomers have spent decades constructing a detailed picture of how galaxies form and evolve, and until recently, that picture seemed sturdy and well supported by data. The Lambda CDM model has accurately described large-scale cosmic structure, the distribution of galaxies across space, and the timeline of growth for much of the universe's history. Yet this galaxy exposes a gap in that framework at its earlier stages, not as a small flaw, but as a profound mismatch. Theoretical predictions and observational evidence are now pulling in opposite directions, forcing researchers to acknowledge that our understanding of the universe's first chapters lacks key components. The early cosmos may have been far more volatile and inventive than the gradual ordered progression that simulations have long portrayed. Scientists now face the prospect that cosmic evolution unfolded with a level of intensity and urgency that our current models cannot yet fully express. Instead of galaxies slowly building themselves piece by piece through mergers, perhaps some regions experienced runaway growth, fueled by physics that operated with exceptional efficiency under primordial conditions. This idea does not undermine the broader successes of cosmology, but it does remind us that even the most sophisticated theories remain provisional, a best attempt to capture the truth with incomplete tools. In this sense, discovery becomes a teacher, guiding us toward deeper insight through contradiction. And nowhere is that contradiction more visible than in the physical interpretation of this galaxy's surprising properties. The immense velocity dispersion, the widespread oxygen signature, the substantial gravitational binding, each measurement points to a system that should require far more than a few 100 million years to assemble. The evidence paints a picture of a galaxy that somehow jumped ahead in line, achieving a level of maturity that defies the strict schedule cosmic physics was expected to follow. It is like opening a history book to the first chapter and finding not primitive scribbles but an already thriving metropolis. Faced with these revelations, some theorists have begun exploring radical possibilities. Could the early universe have experienced pockets of star formation entirely unlike anything we see today? Might exotic processes such as enhanced cooling through unknown molecular pathways or interactions between dark matter particles have triggered sudden collapses of gas into dense starburst regions? There is even speculation that the seeds of supermassive black holes may have been present extraordinarily early, shaping their environments not as destructive monsters, but as engines that accelerated gas collapse and stirred the surrounding medium into overdrive. In most galaxies today, black holes are associated with quenching star formation, but under extreme densities their influence might instead have catalyzed intense bursts of growth. These ideas were once considered fringe scenarios. Now they are being discussed openly as plausible mechanisms that could help explain how the universe built so much so quickly. This is the nature of scientific revolutions, not the abandonment of what came before, but the expansion of possibility to include new forms of understanding. Still, the progress is not solely theoretical. Observational strategies are evolving rapidly in response to Webb's findings. Astronomers are now prioritizing spectroscopy at the highest redshifts to map chemical signatures across cosmic time. Deep gravitational lensing programs are being enhanced to probe galaxies even fainter and more distant than this one. ALMA and other radio observatories will continue to track molecular gas, illuminating how fuel flowed into galaxies during their explosive early phases. Future space telescopes already being planned will push even deeper, targeting redshifts beyond what Webb can reach, and extending our reach into epochs closer to the Big Bang than ever before. Every new instrument will be guided by the lessons learned here. Expect speed, expect complexity, and expect surprises. This galaxy has shifted the mindset of an entire scientific field. Instead of asking whether rapid enrichment is possible, researchers now ask how common it might be and what caused it to emerge so early. Perhaps galaxies like this are rare cosmic prodigies, one in a million cases where everything aligned perfectly for accelerated growth. Or perhaps they represent a previously hidden norm, a sign that the young universe teemed with giant star factories that have remained concealed until the right technology arrived. Either scenario is transformative. If rare, this galaxy demonstrates that cosmic evolution permits exceptions of staggering magnitude, and we must understand what triggers them. If common, the foundation of early cosmic models must be rewritten to account for a universe that wasted no time stepping into complexity. For now, the only certainty is that this discovery has permanently expanded our sense of what is possible. It reminds us that the universe does not operate according to human expectations. It evolves according to the laws of physics, some of which we may only now be beginning to grasp. In the cosmic dawn, creation did not hesitate. It burst forward with extraordinary force, forging galaxies rich with starlight and heavy elements before the universe had even taken its first billion breaths. And as Webb continues to scan the distant darkness, we stand ready for more revelations that will challenge our confidence, reshape our theories, and deepen our awe for the universe we call home. While much of the excitement surrounding this discovery centers on the galaxy's physical properties, another critical component lies in the techniques used to measure them. Spectroscopy serves as the ultimate authority in confirming a galaxy's distance and composition. By analyzing how the wavelengths of light stretch due to cosmic expansion, astronomers can calculate redshift with extraordinary precision. In this galaxy's case, the sharp spectral signature of oxygen provides an unambiguous marker, eliminating the ambiguity that sometimes clouds high redshift observations. These precise measurements anchor the system firmly at a time when the universe was still extraordinarily young. Webb's instruments do more than just measure distance. They dissect the galaxy's very makeup, revealing the distribution of elements manufactured in the hearts of stars. This allows scientists to read a timeline encoded in the galaxy's own atoms. If hydrogen and helium alone were present, as expected for the earliest galaxies, the story would be simple, a system still untouched by stellar chemistry. But the detection of oxygen means multiple stellar generations have already lived and died, spreading freshly forged metals across the galaxy. Spectroscopy thus acts like an archaeologist of the universe, unearthing evidence of ancient processes that took place at inconceivably early times. And while these chemical fingerprints alone would be remarkable, their interpretation in conjunction with the galaxy's luminosity and dynamical mass creates a puzzle that the current theoretical framework struggles to solve. The uncertainties that once gave theorists room to maneuver have now been minimized. Gone are the days when faint early galaxies could be dismissed as misclassified or magnified by gravitational lensing. Here we have a system that stands boldly in defiance of expected cosmic timelines. Its light is too strong, its mass too high, and its metals far too abundant to align with the slow, hierarchical growth narrative. This single observation forces cosmologists to confront the possibility that the universe's blueprint requires more complexity than previously believed. It is as though a rulebook for the early cosmos has been uncovered, but its pages do not match the additions scientists have studied for decades. And while this discovery presents a significant challenge, it also opens a pathway to new understanding, because theories evolve best when they are forced to adapt to undeniable facts. The reliability of Webb's instruments and methods also infuses the field with confidence to ask bolder questions. If one ancient galaxy exhibits such maturity, how many others might be revealed as the data continues to deepen? Each new observation becomes a test. Does it confirm the anomaly or dilute its significance? Early signs indicate that this galaxy may not be alone. Already, Webb has identified additional candidates at similarly extreme distances objects, showing brightness and structural features that hint at accelerated early growth. While many await spectroscopic validation, their existence strengthens the argument that the young universe was far more energetic and productive than standard models allow. If this trend continues, it could redefine the nature of cosmic dawn. Instead of isolated specks of light slowly organizing into structure, it may have been an era of fierce illumination, where giant star factories ignited nearly simultaneously across the cosmos. This perspective radically alters our understanding of how quickly small irregularities in the early universe transformed into sprawling galaxies, and it suggests that the processes that laid the groundwork for later cosmic structure, the very processes that eventually led to the Milky Way, to Earth, to life, were set in motion much more abruptly than anticipated. Meanwhile, theorists are already revisiting long-standing assumptions about how star formation scales with density, temperature, and metallicity in extreme environments. Could stars form in much larger clusters under primordial conditions, yielding rapid enrichment cycles? Could cooling channels involving molecules like hydrogen deuteride have provided unexpected efficiency at early times? Or might new physics be required to explain how dark matter facilitated a faster collapse of gas clouds? These questions stretch across multiple fields, calling for interdisciplinary cooperation between cosmology, particle physics, and experimental astronomy. Even now, there is active debate over what should constitute a reasonable revision to theory. Some push for incremental adjustments to existing models, while others argue for more radical rethinking. The correct path will likely emerge through a combination of both, guided by forthcoming datasets that reveal which explanations endure under scrutiny. For the moment, what's certain is this: every photon Webb has captured from this distant galaxy acts as a catalyst for progress. The shockwaves of discovery ripple outward, stimulating innovation in both observation and simulation. As we learn to decode the messages carried through space and time by ancient starlight, our view of the universe's first moments continues to sharpen. In that sharpening, the origins of cosmic complexity come into focus not as a slow unfolding, but as a dynamic burst of creativity. This galaxy stands as compelling evidence that the universe, from the very beginning, possessed a profound drive to build structures rich with potential, structures capable of evolution, transformation, and ultimately consciousness. And so, this discovery does more than rewrite astrophysical timelines. It deepens our understanding of how quickly the conditions for life may emerge in the cosmos. In witnessing such early chemical maturity, we gain insight not only into distant galaxies but into our own eventual existence. As this extraordinary galaxy forces cosmologists to revisit their assumptions, it also highlights a vital truth about exploration. Progress often depends on instruments that grant us entirely new eyes on the universe. Before Webb, the earliest galaxies visible to telescopes appeared faint and primitive, leading scientists to believe that the first stages of galactic evolution were slow and tentative. But that conclusion may have been shaped as much by observational limitations as by reality. With each improvement in our ability to detect and analyze distant light, the universe has revealed that it was far more active in its youth than earlier images implied. Webb's infrared capabilities allow it to peer through the cosmic veil that obscured early star formation, revealing galaxies in the midst of intense dynamic growth. This single discovery exemplifies a broader theme. Whenever humanity enhances its tools of perception, the cosmos expands its mysteries accordingly. What once appeared as a quiet, uneventful beginning now looks like a time of dramatic transformation, when galaxies competed to forge the first elements and flood the universe with light. In this sense, the young cosmos resembles a wild frontier more than a calm cradle, an environment where gravity, gas and radiation collided in chaotic bursts of creation. This re-evaluation of cosmic history reshapes our understanding of the present. If galaxies formed quickly and efficiently at early times, then large-scale structure across the universe may have reached maturity sooner than expected. Galaxy clusters, cosmic filaments, and the web-like distribution of matter might have emerged in a compressed time frame. Even the supermassive black holes that power quasars once thought to require long periods of steady growth must have found ways to form rapidly, suggesting new insights into how such enormous objects first took shape. Every aspect of cosmic history, from dark matter behavior to stellar feedback to the timeline of chemical evolution, becomes newly subject to scrutiny. The implications extend to topics as intimate as the origins of planetary systems. Heavy elements like oxygen and carbon are essential building blocks for rocky worlds and living chemistry. To find them so early suggests that the universe may have been preparing the conditions for planets and potentially life much earlier than we imagined. Though this does not imply life existed at such early epochs, it does hint that the seeds of habitability began to form quickly once stars ignited. We may need to update our expectations about how widespread complex chemistry could be across space and time. This ancient galaxy provides a vivid reminder that the mechanisms enabling life's eventual rise were set in motion almost immediately after the universe's birth. And this revelation invites us to question whether the pathway to complexity is a rare cosmic privilege or a natural outcome wherever conditions resemble those in the cosmic dawn. That is a philosophical challenge as much as a scientific one. Meanwhile, astronomers eagerly await further observations. As Webb collects deeper exposures, it will reveal more galaxies at this epoch and provide higher resolution insights into their structures. Detailed imaging may show whether this galaxy is rotationally ordered like a spiral, or chaotic like a merger remnant, or perhaps something entirely different from today's familiar morphologies. ALMA will continue to map the distribution of cold gas within the system, clarifying how fuel is being fed into newborn stars. Future missions, such as the Nancy Grace Roman Space Telescope, will expand the search to wider fields, enabling statistical studies that determine how typical such galaxies truly were. As the sample size grows, the theories must adapt. Any successful model will need to reproduce not only this one galaxy's properties, but also the broader diversity of systems Webb uncovers. Scientists expect that new frameworks will emerge that blend elements of current hierarchical models with more dramatic, rapid scenarios triggered by conditions unique to the early universe. The real answer will likely be more intricate than any single current proposal. In all of this, the guiding principle remains clear. The universe is the ultimate authority, and observation is its voice. Theories that once appeared immovable must shift when confronted with new truths carried by ancient light. And there is poetry in that process. Our expanding knowledge reflects the very expansion of the cosmos, as understanding stretches out to match what the universe reveals. This galaxy is more than a scientific oddity. It is a beacon signaling that the first ages of existence were rich with invention, and it embodies a core lesson of discovery. The universe always has more to teach. Just when we think we've mapped the boundaries of possibility, a deeper look transforms the landscape. The cosmos was never simple. Not at the beginning, not now. And this remarkable galaxy stands as proof that complexity is woven into the universe's fabric from the very start. One of the most profound implications of this discovery is that it challenges a deeply rooted expectation in astrophysics, the assumption that complexity arrives only after long periods of gradual development. For decades, scientists have modelled the universe's evolution as a slow crescendo, beginning with isolated pockets of star formation and steadily building toward the majestic galaxies seen in the modern cosmos. But this ancient system disrupts that comfortable narrative. It suggests that the universe did not meander towards structure, it leapt. Within what seems like an instant in cosmic terms, matter organized itself into a sprawling star-filled entity rich in heavy elements. This idea forces us to contemplate that the cosmos may be inherently driven toward complexity from the moment it became transparent to light. Instead of a timid unfolding, the early universe may have embraced a kind of explosive ingenuity, forming systems that defy the constraints we believed fundamental. And this is not merely a curiosity about one object. It may reveal an essential truth about how the universe operates under extreme initial conditions. When matter densities were highest, when gas was most abundant and dark matter halos were forming at breakneck speed, galaxies might have emerged as rapid overachievers, accelerating the march toward diversity and chemical potential. This possibility casts the earliest universe in a new light, not as a dark and empty waiting room, but as a cauldron of intense activity. That concept resonates deeply with the story of cosmic evolution. The galaxies we observe today, rich in structure, adorned with billions of stars, owe their existence to these first luminous pioneers. The rapid appearance of heavy elements like oxygen is especially telling. These atoms form the essential ingredients for molecules that cool gas efficiently, enabling the formation of increasingly intricate structures. And so, the presence of such elements within only a few 100 million years of the Big Bang implies that the first steps toward complexity, including the potential foundations for life-supporting chemistry, began astonishingly early. Heavy elements are the universe's toolkit for transformation. Their widespread existence in this galaxy tells us that nature quickly assembled the raw materials needed for future architectural feats. The universe was not content to remain simple for long. It pushed toward the diversity that would one day include planets, ecosystems, and conscious observers capable of wondering how it all began. This realization carries a philosophical weight that reaches beyond equations and models. It suggests that complexity is not a miracle reserved for late epochs, but an intrinsic aspect of cosmic evolution. The seeds of our own existence were planted almost the moment the universe could sustain them. That does not imply life existed then, but it does indicate that the preconditions for life were assembled at remarkable speed. And if that is the case here, in a corner of the cosmos now viewed only through faint photons after 13.4 billion years of travel, how many other ancient galaxies may have followed similar paths? How early might the universe have been capable of generating environments suitable for habitable worlds? These questions stretch the imagination into realms where science and wonder converge. Meanwhile, this discovery strengthens the role of high redshift astronomy as a cornerstone of future research. Webb has proven itself a gateway to the deepest past. The more we search, the more evidence accumulates that the standard timeline for cosmic evolution lacks the full range of possibilities. Theorists will continue to refine simulations, incorporating new physics if necessary, until the models align with what the universe is revealing. It is likely that as more galaxies of this age and maturity are confirmed, some of the most foundational assumptions about what controls star formation and chemical enrichment must be rewritten. Perhaps the earliest galaxies were formed in intense bursts triggered by gravitational instabilities we have not fully understood. Perhaps cooling pathways in primordial gas were more efficient than assumed. Or perhaps dark matter played a more dynamic role in the young cosmos, helping matter assemble rapidly in places of exceptional density. In any case, the path forward demands creativity. It demands that scientists remain open to radical ideas while rigorously testing them against observation. This galaxy stands as a challenge and an invitation to push the boundaries of what is scientifically conceivable. It also highlights how extraordinary progress can emerge when advanced instrumentation meets bold curiosity. Humanity built a telescope capable of seeing farther into time than ever before, and the universe rewarded us with a discovery that reshapes our cosmic origin story. The message carried across the abyss of space and time is clear. Complexity was not late to the party. It was present almost from the beginning. And now that we have glimpsed its signature in one corner of the early universe, we are compelled to continue the search, to reveal the full extent of this ancient creativity. The cosmos, it turns out, has always been an ambitious architect constructing brilliance at the earliest opportunity. As the implications of this discovery continue to unfold, scientists also recognize its value as a calibration point for interpreting the distant universe. Every distant galaxy Webb uncovers must be assessed through the lens of what we now know is possible. Long-standing assumptions about size and brightness thresholds for high redshift candidates must be reconsidered, because we now have concrete proof that massive, chemically enriched systems already existed extremely early. This means that future surveys cannot simply filter out bright or unexpectedly evolved galaxies as likely being closer or lens magnified. Instead, astronomers must accept that some of the universe's earliest chapters included galaxies that reached maturity with astonishing speed. Already, Webb's deeper observations are revealing additional candidates that might match or even surpass this one in mass and luminosity. If confirmed, those systems would expand the list of early cosmic overachievers and give theorists a larger data set with which to construct new models. The scientific momentum is shifting. Instead of searching for faint beginnings, researchers are preparing to map a cosmos that exploded into form almost as soon as the physics allowed it. In practice, this means a broad rethinking of what drives early galaxy evolution. Traditional narratives emphasize the slow accumulation of matter through mergers over time, but this discovery suggests that growth mechanisms may have been more efficient under primordial conditions than in later eras. Gas was more abundant, densities were higher, and space was smaller. Physical settings that could create opportunities for rapid collapse and intense bursts of star formation. Dark matter halos forming earlier and deeper than expected might have acted like gravitational engines, pulling in gas at extreme rates. And once the first round of supermassive stars enriched the environment with heavy elements, the door opened for even faster growth, powered by newly enhanced cooling and recycling cycles. This paints the early universe as a place of accelerated transformation, where every step toward complexity triggered the next in rapid succession. In this sense, the discovery supports a view of cosmic history that is not linear but exponential, an early surge followed by a long period of refinement. This shift in perspective has consequences for how we view everything from the Siam reionization era to the origins of galactic structure. If large galaxies formed early and radiated vast quantities of ultraviolet light, they may have played a dominant role in stripping electrons from hydrogen across the universe, ending the cosmic dark ages sooner than predicted. It also suggests that galactic ecosystems where chemical enrichment, gas flows and star feedback intertwine developed within a much narrower time frame than once assumed. This revelation challenges theorists to design models capable of capturing these rapid, interconnected processes without violating fundamental physics. And while solving that puzzle will require time and innovation, The discovery has already succeeded in its first essential task, exposing the limits of our current understanding. Every major advance in astronomy has been driven by similar tensions between theory and observation. The discovery of quasars forced recognition of supermassive black holes. Observations of distant supernovae revealed the accelerating expansion of the universe. Now this ancient galaxy stands as the next milestone, a reminder that the cosmos always contained surprises that challenge scientific certainty. In grappling with these mysteries, researchers are guided by a profound message embedded in every photon that reaches us. The universe is not merely older than we can easily comprehend, it is also more creative in its youth than our theories once allowed, and this creativity has consequences that extend far beyond astrophysics. Rapid chemical enrichment implies a profound truth. The universe was manufacturing the elements essential for planets, oceans, and life almost immediately. Though it would take billions of years before such elements assembled into living systems, the foundational chemistry was already in motion during the first sliver of cosmic time. Our origins, therefore, trace back not only to later, familiar galaxies like the Milky Way, but to the explosive brilliance of these early giants. They were the first architects of complexity, the ones that forged the universe's potential into reality. Science and existential reflection intertwine here. The earliest stars gave the cosmos the capability to build observers who could one day look back and ask where it all began. And in answering that question, we have discovered that the universe's ambition did not sleep. The blueprint for everything that would follow was rapidly drafted under the glow of these primordial starburst galaxies. Because of this, the study of the universe's first few 100 million years becomes more than a technical pursuit. It becomes a study of the roots of creation itself. The discovery of this mature galaxy at such a staggering distance invites us to reconsider not only how quickly the universe evolved, but how quickly meaning emerged from the void. Even as this discovery energizes the scientific community, it also underscores the importance of embracing uncertainty as a driving force for progress. Observations like these remind us that the cosmos is the ultimate laboratory, one far richer and more inventive than any simulation. When astronomers craft models of the early universe, they must make educated assumptions about how quickly gas cools, how dark matter behaves, how efficiently stars consume their fuel. These assumptions have worked remarkably well for most of cosmic history, but this galaxy reveals a spot where those assumptions fail. Rather than a sign of weakness, this conflict is a call to innovate. It forces us to explore new physics, to question hidden biases embedded in our models, and to revisit the earliest moments after the Big Bang with fresh curiosity. The next generation of cosmological theory will not discard the successes of the current framework. It will build on them by filling in the gaps exposed by discoveries at the cosmic frontier. Those refinements may lead to surprising revelations. Perhaps gravity behaved subtly differently under the extreme densities of the cosmic dawn. Perhaps early dark matter interactions triggered rapid collapses in ways we do not yet understand. Or perhaps our equations governing star formation must evolve to include processes that only occur under the harshest primordial conditions. But however explanations change, they will be driven by truth delivered directly from the universe itself. And the truth here is indisputable. Complexity emerged swiftly, repeatedly, and in unexpected places. New observations will continue to sharpen this message. Webb will push deeper into time, ALMA will map cold gas in greater detail, and upcoming missions will reveal the surroundings of these early galaxies, showing whether they formed in crowded neighborhoods or stood as isolated overachievers in the cosmic wilderness. The search for even older systems, those existing less than 250 million years after the Big Bang, is already underway. And each detection has the potential to redraw the boundaries of the possible. The era in which scientists simply extrapolated from known galaxies is over. We have now entered a phase where direct observation of the first major structures will determine the shape of cosmic theory. This shift has cultural as well as scientific significance. Humanity has always asked how the heavens began. Ancient civilizations looked to the stars for origin stories. Now we read those stories in the language of physics and distant light. Yet the impact is no less profound. When we discover that the universe was forging advanced structures almost immediately, it changes our perception of existence. It suggests that the cosmos has always carried within it the capacity for creativity, rapid, explosive, and resilient. And it reminds us that complexity is not something fragile or rare, but something inherent, arising naturally whenever the conditions allow. That understanding enriches our perspective on the world around us. The oxygen we breathe, the carbon in our cells, the calcium in our bones, all were manufactured in stars, and the earliest chapters of that alchemy began far sooner than we once believed. In studying this galaxy, we are studying the ancestry of the elements that sustain life. We learn that we are connected not only to the Milky Way, but to galaxies that lived and shone when the universe was younger than a single heartbeat in cosmic time. These discoveries also emphasize the profound resilience of curiosity. Humans built a machine capable of collecting ancient starlight, deciphering its chemistry, and measuring its motion across billions of years. That feat represents a triumph of technology, mathematics, and imagination working together to explore the deepest questions of existence. And now that Webb has revealed this first glimpse of the universe's explosive youth, we must rise to the challenge of interpreting it. Every new image from the early cosmos becomes a spark, a test of our ability to adapt our understanding and expand our vision. Already new generations of scientists are being inspired to explore the frontier of cosmic dawn, driven by the promise that every observation may overturn a piece of what we thought we knew. That is the heart of scientific discovery, not certainty, but the continuous refinement of truth. And this galaxy, shining to us across 13 billion years of expanding space, embodies that spirit perfectly. It stands as a testament to the idea that the universe holds greater wonders than we have yet imagined, and that the pursuit of knowledge is a journey with no final destination, only deeper horizons. As we prepare for what Webb will uncover next, we do so with renewed humility, renewed excitement, and an unshakable sense of awe. For we now understand, the early universe was not a blank canvas gradually filled in over time. It began as a masterpiece already in progress. In the end, this remarkable galaxy represents far more than a single point of data plotted on a graph. It is a reminder that the universe's earliest eras remain largely uncharted territory, full of surprises that overturn long-held assumptions. The discovery compels us to rethink how swiftly matter assembled into complex structures, how rapidly the first stars forged heavy elements, and how energetically the cosmic landscape lit up after the primordial darkness. The fact that such a chemically enriched system existed when the universe was only a few 100 million years old forces us to question whether the traditional timeline of hierarchical growth reflects reality or merely the limits of earlier observations. It suggests that the cosmos, in its infancy, may have operated under conditions that encourage rapid leaps toward higher levels of organization. Future research will determine whether this galaxy is an extraordinary anomaly or a representative of an entire class of early systems waiting to be uncovered. If more examples emerge, the field will undergo a fundamental shift in its understanding of how galaxies form, giving rise to new models that embrace accelerated early growth, intense starbursts, and widespread chemical enhancement long before the universe reached its first billion years. Scientists anticipate that Webb will continue revealing more early giants hiding just beyond the reach of previous instruments, each new detection adding detail and dimension to this evolving narrative. But even if this galaxy remains a rare outlier, its existence alone is enough to redefine the boundaries of possibility within cosmic evolution. It proves that the universe does not always follow predictable trajectories. It takes risks, if one can use that word in experiments with extremes, producing results that challenge the neat categories science constructs. And in doing so, the universe invites us to expand our imagination, to revise our expectations about where complexity can arise and how quickly it can flourish. The significance of this discovery extends beyond technical papers and theoretical debates. It deepens our philosophical relationship with the cosmos. To know that stars capable of forging oxygen, carbon, and other life-essential elements existed so early is to understand that the universe developed the ingredients for biology almost as soon as it had the ability to do so. The atoms within every living organism can trace their ancestry back not just to ancient stars, but to the very first generations of stellar furnaces that ignited when the cosmos was still young and unrecognizable. That connection across time is profound. It underscores the idea that life is woven into the cosmic story from a surprisingly early chapter. We are the product not only of billions of years of evolution on Earth, but also of the universe's rapid drive toward complexity from its very beginning. And as we gaze deeper into space, we are literally looking backward in time toward the forge that shaped our existence long before Earth was born. This ancient galaxy serves as a mirror in which we glimpse our own distant origins. Its starlight, stretched and softened by expanding space, carries with it a message about resilience, transformation, and emergence. The message says, complexity is not a fluke. It is a natural expression of the universe's laws. The discovery encourages a renewed sense of wonder in humanity's search for meaning. Every step forward in astronomy reminds us that knowledge does not diminish mystery. Rather, it expands it. The deeper we look, the more we learn, and the more questions emerge, each one an invitation to explore. We build ever more powerful telescopes not to exhaust the unknown, but to deepen our relationship with it. This galaxy, shining from the dawn of time, assures us that the universe has always been a dynamic place, creating new wonders faster than we can catalogue them. It tells us that the cosmos is not a passive backdrop for existence, but a living, evolving environment rich with surprises. And with every discovery like this one, we stand a little closer to understanding how everything began, not slowly, not timidly, but with extraordinary brilliance and ambition. As Webb continues its mission, and future observatories join the pursuit, humanity will keep listening to the stories encoded in ancient light. There will be more revelations, more challenges to our theories, and more awe-filled moments when the universe proves that reality exceeds imagination. This galaxy, emerging so early and so impressively, is a milestone in that journey, a landmark at the frontier of knowledge. It reminds us that the cosmos is far more dynamic and creatively driven than we ever dared to assume. And perhaps the most inspiring truth of all is this: if such grandeur existed at the universe's beginning, then its future possibilities are limitless.